So the barn is the conventional unit for nuclear cross-sections. It's a historical name, and I think I told some students the other day, the way it originated supposedly is when people first started measuring nuclear cross-sections, they had an idea that the cross-sections would be similar to the physical dimensions of the nucleus. So they were expecting cross-sections of 10 to the minus 26 square centimeters or so, and they started out doing neutron capture cross-sections, which turned out to have especially large values. And so when they measured these cross-sections, they were surprised how big they were, and supposedly someone said, my God, it's as big as a barn. And that's how the name originated. At least that's what I learned when I was taking this class. So these are the units we're going to use. Again, a useful thing to remember, I would probably tell you that a barn is 10 to the minus 24 square centimeters. The kind of nomenclature we use to write down reactions is sometimes confusing because it's written in a couple different ways. So I think I've probably written down reactions that look like this. A plus B, where one of them is the projectile, one is the target. It really doesn't matter. Make some other nuclei C and D. And an example might be calcium-48 plus an alpha particle makes scandium-51 plus hydrogen, okay? And something you might want to check is that, in fact, I'm not cheating you here, that this is a legitimate reaction. How would you tell if that's a legitimate reaction or not? What criteria would I look for? Check the number of neutrons and protons. That's right. What is the number of protons on this side of the equation? Is it the same on the other side? Let's go through it. How many protons in calcium-48? You got a periodic table handy? Okay. You know where to look it up. It's 20. Calcium's element number 20. How many protons in a helium-4 nucleus? 2. Okay, so we got 22 protons on the left-hand side of the arrow. It turns out scandium has 21. And how many in a proton? 1. So we got 22 protons. And again, you go through the arithmetic on the neutrons, it'll work out. So that's what you want to check for to see if it's a legitimate reaction. If it doesn't balance, something's fishy. That can't happen. Because in these kind of reactions, we don't create or destroy neutrons or protons, we just rearrange them. What is an example of something we've talked about where we do change the numbers of neutrons and protons from the left-hand side of the arrow to the right-hand side? Beta decay. Beta decay. Perfect. Right. There we're taking a neutron and turning it into a proton, or vice versa. But even in beta decay, the total number of neutrons and protons, that is the A, doesn't change. We convert a proton into a neutron or vice versa, but the total number of neutrons and protons is left unchanged. What's the other thing I'm going to check for on a reaction like that or in a radioactive decay? What else has to be the same before and after? The charge, exactly. So here we're okay because the number of protons basically is a measure of the charge. In the beta decay, I take a neutron, I turn it into a proton, and if that's all that were emitted, that would violate conservation of electric charge, and we don't think that happens. But we know that there's a beta particle, a negatively charged electron that's emitted, and that balances the positive charge of the proton, and we end up starting with something electrically neutral, ending up with something electrically neutral. You want to check for those things. Okay, the other way of writing the same information is sometimes written like this, and I think Lily wrote it like this in one of your homework problems. You write A, little b, little c, d, and it means the same thing. So in this case, I think the homework problem had to do with neutron capture on chlorine-35, producing chlorine-36 plus a gamma ray. I mean, you could equally well write it like that, but these are just different, shorthands, if you like, for these nuclear reactions, and you should get comfortable with either way of looking at it. The concept of cross-section can be developed in a little more detail in that, in addition to asking just how many reactions happen, I can ask more specific information, like if I have a beam coming in from left to right, and I stick a detector at a certain angle relative to that beam, how many particles am I going to see? And how will that vary as I move my detector around and vary that angle that I'm calling theta? And so this introduces the concept of what we call a differential cross-section, a cross-section that's a function of angle. And so what we're doing now is moving from rectangular kind of coordinate thinking into these spherical coordinates. So we have two angles that we need to think about. There's the polar angle theta, which I'm measuring from the beam direction as indicated here, and then phi is the angle around the beam direction, okay? And usually we only consider the one angular variable theta as being important. It turns out that if the spins of the nuclei are random, then that integration integrates just to a factor of 2 pi. So I'm imagining I have a detector that's sitting over at some angle relative to the beam, and the detector has a certain area that it occupies. So I have a little circular area detector sitting over here, and it's staring back at my target, which is in green, and the idea is the target is presenting a certain cross-section to the beam, and occasionally a beam particle will go through that target and be scattered or produce a particle that goes off at the angle theta. And are you guys familiar with the concept of solid angle? Hopefully. You heard that term before? Okay, so the idea is if I have a sphere, what's the surface area of the sphere? 4 pi r squared. Okay. I think of the surface of a sphere in terms of these two angles, theta and phi. I think of them as making a square area on the surface of the sphere. And what we call the solid angle is this area in angular dimensions, because on the surface of the sphere, every point is the same distance from the origin. They're all a distance r from the origin. And what distinguishes them from one another is the angle with respect to a coordinate system I set up at the origin. So we say that the solid angle of a sphere is 4 pi, and the units we use are called steradians. You've heard of radians, I hope? Another way of measuring an angle. Well, a steradian is a square angle. So it's basically a product of delta theta, delta phi, with a factor of sine theta thrown in. So this d omega is what we're calling the solid angle that my little detector subtends. And it's essentially the fraction of the total area of the sphere which is covered up by my detector. Okay? And multiplied by 4 pi because I arbitrarily say there are 4 pi steradians in a sphere. So the total cross-section is the integral of this differential cross-section over all the possible angles the particle can go off at. So my differential cross-section I call d sigma d omega. That's the cross-section per unit solid angle, per unit square angle. I multiply it by d omega, which is sine theta, d phi, and I perform this integration where theta goes from 0 to pi, and it turns out phi goes from 0 to 2 pi, and you end up getting that the total cross-section is this integral of the differential cross-section. Now, if the cross-section is independent of angle, that is, if it doesn't matter which angle I sit at, my detector always sees the same number of particles, this term is a constant and comes out of the integral, and I end up basically just getting a factor of 4 pi when I do that integration. I would get 4 pi times whatever that number is. Okay? There's going to be a homework problem this week which makes use of some of this information. That's why I'm going through it. If you have troubles with it, come see me or come see one of the TAs. Let's just go through a simple example which is closer to the kind of problem you had on your homework already, and see how we use the idea of a total cross-section to calculate something. So I'm going to consider the reaction shown up here. It's the reaction of helium-4 with beryllium to make carbon-12 plus a neutron. And you can go ahead and check later on that, in fact, this is valid because it conserves proton and neutron number. And I say the cross-section for this reaction at an energy, and what I mean by that is the kinetic energy of the helium-4 particle is 10 million electron volts. And at that energy, the cross-section somebody has measured turns out to be 700 millibarns. So 0.7 barns is the cross-section. And the way I'm stating this problem is the way an experimental nuclear scientist might think about it, which is what I am. So we'd say if a 1 milligram per square centimeter beryllium-9 target is bombarded with 1 microamp of beam, how many neutrons get produced a second? So you have to sort of digest the information that's being given there and try to sort out what you need to figure out what's being asked of you. So I'm telling you in a slightly convoluted way how many target nuclei there are. I'm saying it's a milligram per square centimeter. So that number is the mass of the target as viewed by the beam going through it. So it's the mass, it's the density of the target times the thickness, really. Okay, but I need to convert that into the number of atoms. Similarly, I'm telling you a current for the beam. And what I'm saying is each helium-4 nucleus has had all of its electrons removed from it, so it has a charge of 2 units in units of the electron charge. So I'm going to use this formula rewritten just a little bit from the way I had it a minute ago. This is the way Lilly writes it. So the rate of these reactions, the rate of the number of neutrons being produced, is the current expressed in appropriate units. That is, how many helium-4 nuclei I'm shooting at the target per second, times the cross-section, times the number of targets. And let's just see if this is going to work out. This is going to be a number per second. It's the number of helium-4s per second. This is a cross-section, which is going to have units of area. And the way I've written this, this is the number of targets per unit volume times the thickness. So this is going to end up being a number per square centimeter, number per unit area. So the areas will cancel out, and I'll end up with just a number per second, which is what I want. Okay? So I take a microamp, that's 10 to the minus 6 coulombs per second. I divide it by the charge that each helium-4 carries, which is 2 times the fundamental charge, 1.6 times 10 to the minus 19 coulombs. I convert 700 millibarns into square centimeters. It's 7 times 10 to the minus 25. And then I calculate how many atoms there are per square centimeter by taking this mass per square centimeter, dividing by the atomic weight of beryllium, and multiplying it by Avogadro's number. And when I'm all done and multiply those together, I get the rate of neutron production is 1.46 times 10 to the 8th a second. Okay? That's the kind of problem I'm going to expect you to be able to do. And we'll give you various combinations of these quantities and expect you to calculate the others. Okay. I'm going to spend 2 more minutes introducing the area we're going to go into next week. Then we'll take a break, and then we'll have a problem session. So I've mentioned before this idea of forces. And it turns out we've identified 4 separate kinds of forces in the universe. The first one, you're all familiar with gravity. Okay? It's the thing that makes the planets go around the sun. It makes the apples fall on Newton's head, all that kind of stuff. The other one that was discovered classically is electromagnetism. Okay? The thing that holds the atoms together is the electrostatic attraction of positive and negative charges. Magnetic fields are produced as a result of moving electric charges, and so on. The last 2 forces were not discovered until about 100 years ago. And they are the things that are mainly the topic of this course, the strong and the weak interaction. The strong interaction historically was also called the nuclear interaction. It's a little bit fuzzy today exactly what we mean by that. In this class, what we mean usually, it's the force that's holding the neutrons and protons together inside an atomic nucleus. It's the attraction or repulsion between the neutrons and protons. And then the other force, which again was only discovered somewhat recently, is what we call the weak interaction. This is the one which is responsible for beta decay and is also responsible for the reason neutrinos are so weakly interacting. The way we imagine all of these forces taking place, I've also indicated, is through the exchange of particles. Okay, what we think of going on in gravity is that the Earth and me and you are continually exchanging particles. Okay, they happen to be called gravitons. No one's ever seen a graviton, but we think they're there. We believe they have 0 mass, and as a result of that, the range of the gravitational force is infinite. Similarly, the way we picture electromagnetism working is that objects are continually exchanging photons back and forth. And again, the photons have no mass, and as a result, the range of the electromagnetic interaction is also infinite. The strong and the weak are different in that the particles which are being exchanged actually have rest masses, and quite large rest masses. In the classical way of thinking of the nuclear interaction, we think of pions as being the particles which are exchanged. The pion is a real particle. You can produce them in the lab. They have masses of about 140 MeV over c squared. And if you think about it a little bit, you'll realize that mass sets the distance scale over which the strong force can work. And it turns out, we'll go through this later, it's about a femtometer. Okay? And that makes it very different than the electromagnetic or gravitational interactions in that it has a very, very short range, meaning you got to get nuclei very close together or nothing's going to happen. And the weak interaction is even more extreme in that sense. The particles which mediate the weak interaction weigh as much as a germanium nucleus. Okay, these are big, heavy things, 80 or 90 GeV over c squared. And what that means is the range of the weak interaction is even smaller, and that's why it's so weak, because particles have to get really, really close for anything to happen. And the way we think about these things, again, sort of semi-classically, is in terms of these diagrams, and you don't have to write this down or be able to do anything with it, but it's sort of a nice picture to have in your mind of what's going on. And the first one is electromagnetic. So this is just the Coulomb repulsion, the electrostatic repulsion of two electrons. Why is it that it's hard to bring these like charges together? Well, it's because they're exchanging these photons back and forth. And the idea of these diagrams is that time is sort of running from the bottom to the top, and each one of these lines represents the trajectory of a particle. And so here's an electron and here's another electron, and they're kind of moving towards each other. And the way they talk to one another is by spitting these photons back and forth. And it turns out that these two electrons repel each other, and so they move off in opposite directions. Now, you might say, well, that makes sense. I can imagine that classically. The classical analog is I've got two people standing on an ice rink, a nice smooth ice rink, and they're throwing a baseball back and forth. So if I throw a baseball to you, when I release the ball, what's going to happen to me? I'm going to go backwards, because of conservation of momentum. I throw a ball that way, I go this way. When you catch it, what's going to happen to you? You're going to go backwards. You're going to move in the same direction the ball was. And so the net result of us throwing that baseball back and forth will be what? What will happen to our relative separation? We'll get further and further apart. That's like this repulsion. Okay, that's easy to understand. What you're supposed to be thinking about is, well, gee, how in the heck do you get attraction that way? Suppose I made that an electron and a positron. The diagram would look exactly the same, it turns out. Okay? And yet it would lead to attraction. And there isn't a good classical analog of this, but the one I make up, and I'll give it to you for better or worse, is suppose we do exactly the same experiment, except we're throwing a boomerang. Okay? So you know what a boomerang's trajectory looks like. So if I want to throw it to Brian, who's sitting in the back of the room, I stand like this, and I throw it that way, and I give it a nice twist. So I'm throwing it this way, and as a result, I recoil that way. It moves around in a big circular arc like that and hits Brian in the back of the head and makes him come toward me. And that leads to attraction. So it isn't a perfect analogy, but it's the best I could come up with. Now, the other sort of weird one, yeah. Was that a... Very good, very good. Okay. Let me use this as the example, okay? You're pointing out something very fundamental about this, is that energy is not conserved in this process, okay, at least for a little bit. So here's the nuclear force. This is the way physicists 30 years ago thought the nuclear force worked. Here's a proton, here's a neutron inside a nucleus. They're held together very, very tightly by this strong nuclear force. And the way it was pictured is they're exchanging pions. And the way I've drawn this, I'm imagining a proton is coming this way, a neutron's coming that way. At this point in time, this particle, this proton, spits out a positively charged object, a positively charged pion. Now, there is no uncertainty principle for electric charge. So electric charge has to be conserved all the time. So at this moment, if I spit out something positively charged, I better produce something neutral, which I do. I make a neutron. That's okay. And on the other side, the neutron absorbs that positive charge and turns into a proton. So I've actually caused a proton and a neutron to reverse roles. Okay? But at the end of the day, you can't tell one proton from another or one neutron from another. You can't tell which was which. But what you've pointed out is extremely important. At this point, I've created a particle whose mass I just told you was 140 MeV over c squared. Inside an atomic nucleus, I never have that much energy available. So classically, this is not allowed to happen. It would violate conservation of energy. But remember the uncertainty principle. The uncertainty principle says delta E, delta T is on the order of h bar. And what that means is for a little bit of time, I can cheat. I can borrow energy if I return it very quickly. And what's happening in these diagrams is the uncertainty principle is allowing this to happen. During that very, very short period of time when I can't actually measure it, this particle steals 140 MeV from the rest of the universe, makes a pion, which travels over here and then delivers that energy back. So it's only because of the uncertainty principle that that can happen. And because of that, the range of this interaction is limited. Because what's the fastest that pion can possibly move? The speed of light. And so if you take the speed of light and you plug that into the delta E, delta T, you'll find the maximum range of this thing is about a femtometer. That's where that range came from on the previous slide. So it's the uncertainty principle that lets that happen. And that's why you can't take these pictures too literally, because this is a quantum mechanical thing and we're using very classical pictures to try to get a handle on what's going on. Okay, so we're going to stop for today, and next week we'll start developing more discussion of nuclear forces and how they manifest themselves in nuclei.